Swayam Prabha. Digital India. Educated India.
Tier 101, think and analyze, but actually it's technical arts. So this is lecture number 3 on orthographic views. So first, a few corrections in lab 1. So I realized that these dimensions are a lot smaller for you to work. So you might want to consider these dimensions. So replace 20 mm by 100 mm over here, 15 mm by 75 mm here, over there 20 mm by 100, 15 mm by 75, here 100, so 10 by 100 and 8 by 80, just scale it up, and over there 10 mm by 100 mm. Okay, so these corrections, they should help you draw these ellipses better. Okay, so let's revisit the construction of the ellipse using the 4-center method. So here we have a rhombus, or let's say here we have a parallelogram. So this edge is at 30 degrees with the horizontal. Okay, so as I said, the first thing that you would need to do is draw the longest diagonal first, and then from this vertex join or draw a line segment joining the midpoint of the opposite edge. From here again the same thing, draw a line segment joining the midpoint of the opposite vertex. Okay, so this is center C1, center C2. With this as radius, draw an arc. With this as radius, draw another arc over here. Center C3, draw this arc. Center C4, draw this arc over here. Of course, this arc would be of radius this length, and this arc would be of radius this length. Now let's try to figure something out here. So this length is, let's say, L. So as I said, this is a rhombus. So this length is 2L. Let's assume that this distance is d. Now what is this angle theta here? Now if you look at this construction carefully, if you want this arc to be tangent to this line segment here and this line segment here, so it so happens that this triangle here has to be a right angled triangle. Okay, so the cosine of this angle will be L over 2L, or theta would be the arc cosine of half, which is 60 degrees. So if this is 60 degrees, this angle over here would be 60 degrees, and this and this, these two angles are going to be 120 degrees. You know, just the other way around, just the transformation, rotation transformation. Okay, so now this edge of the rhombus is at 30 degrees to the horizontal. This is 120 degrees. Same thing, draw the longest diagonal first. Okay, from here join the midpoint. From here join, or rather from here join the midpoint. You'll get the centers as C1, C2, C3, C4. You know the construction. You can go ahead and construct this approximate ellipse, not a problem. Okay, now if this angle is anything other than 60 degrees, then what happens? If you follow the same construction procedure, identify the longest diagonal. From here join the midpoint of the opposite edge. From here join the midpoint of the opposite edge. Identify the centers, 4 centers, and complete the construction of the ellipse, what will happen is a part of this arc is going to be away, or is going to be lying outside this parallelogram. This is something that you would not want. Okay, and this would be an exercise that you will be doing extensively when you are drawing circles as ellipses in isometric drawings or projections. Okay, so this angle has to be equal to 60 degrees, otherwise this construction is not going to work. Okay, so let's get into orthographic projections. Okay, second week, third lecture. All right, this is now my 11-year-old. Then I think he was about maybe a few months old, enjoying, has quite a bit of task ahead, trying to look at us and trying to figure, well, find orthographic views, what they are. Let's see. So we have the first object here, and let's try to look at this object from different directions. Okay, so let me take this object onto the top right corner of my screen. Let's look at this object from this side. How does it look? This is how it looks. It's actually a rectangle. Now let's look at this object from the top. How does it look? Again, pretty much like a rectangle. And if I look at this object from this side, it looks like a trapezium. Yeah? Okay, let's take another object. Okay, and let me take it back to my top right corner again. And again, try to investigate how this object looks from the three sides. If I look at this object from this side, looks like a sector. There is Shuklaji behind the object. He is not a part of the object, definitely. If I take a look at the object from the top, how do you think this object is going to look like? Well, you're right, looks like pretty much like a rectangle. And if I take a look at the object from behind, okay, again, looks pretty much like a rectangle. The third example, a little more complex. This object is basically a flat plate over here, a rectangular block over there, and a semicircular block over here, all glued up together in that fashion. All right, so if I take a look at this object from this side, how does it look to you? Yeah, so it looks like a rectangle here, and this would also show up as a rectangle, pretty much like this, a bigger rectangle and a smaller rectangle. And there would be a rectangle corresponding to this block over here on the top. Yeah, so ignore all the other entities behind the object. Yeah, anything else? Possibly not. If I take a look at this object from the top, how would it look to me? Guesses? All right, so corresponding to this main block, I'll see a rectangle, and with regard to this block, I'll see a rectangle somewhere on the top left of this one, and with regard to this semicircular block over here, I would actually see a semicircle, pretty much like this. Yeah, so you have this rectangular big block and a small rectangle here and a semicircle here. And if I take a look at this object from behind, how would it look? Well, so this part would show up as a rectangle. This part would again be a rectangle, and corresponding to the top block, we'll see a rectangle over here. Well, these are actually not perfect rectangles. Why? Because the eye is very, very close to the object. It's not very far, but if the eye is quite far from the object, you'll probably not see the top face as you see in this figure. All right, so the point I'm trying to make is let me go back. Yeah, the point I'm trying to make is, if you have any object at hand, and if you try to look at this object from 3 mutually perpendicular directions, orthographic, okay, you'll essentially get different impressions of the object or about the object. And orthographic projections essentially pertain to those impressions that you have if you look at this object from 3 mutually orthogonal directions. This is the first direction, second direction, and third direction. Yeah? Okay. The first step to comprehension. So, given an object, what do you do? Let's take an example. So, this is a victory stand, gold, silver, bronze. Okay, just an example. So, it's a pretty nice, very simple example. So, it's easier for me to locate the 3 perpendicular axes. Let me call this axis as x, that one as y, and the third one as z. And if I want to investigate how this object looks from different directions, again, so the point is that I'm trying to capture the impression that this object is going to be giving in 3 mutually orthogonal planes. In this case, xy, yz, and xz. Yeah. All right. So the first thing that if I take any object, I feel like rotating, translating, do whatever with this, and try to look at this object from different angles. Yeah. So it happens that only 3 angles are adequate for me to completely describe this object. Something very similar here. So probably I would be rotating this object about the z-axis and see how the object looks like, or the x-axis, see how the object looks like, or the y-axis, and get the impression of the object. Okay, so let's do this. First, let me rotate the object about the z-axis and try to figure how the object looks like. So if I rotate the object about the z-axis, which plane am I looking at? I'm looking at the xz plane. Okay. So I'm looking at the object from this direction. So let's draw the axes. So when you're going to be drawing the orthographic views, I mean, this is just for your understanding, this is just for your comprehension, but essentially when you're drawing the orthographic views, you will not be drawing these axes. It's just for you to understand. All right, so let's look at what we see on the xz plane. Do we see this edge? What would this edge correspond to? It would correspond to the bottom edge of the object. How about the vertical edge here? This would correspond to this edge of the object. How about this edge? It will correspond to this edge, and then the vertical from here to here, and then another horizontal will correspond to this edge, a vertical downward here, a horizontal downward, well, rather a vertical downward, upward from here, and then a horizontal that would represent this edge. Okay. Do you see anything else? Possibly not. Okay. How about if we rotate this object about the x-axis and see what we see? Yeah, see what we see. Essentially, how would the object look if we place our eye over here from the top? So we are looking at now the xy plane. Yeah. Here you go. Now, what would this edge correspond to? It will essentially be corresponding to this edge, and this edge together. So this edge would essentially be appearing as a point somewhere on the edge here, and this vertical edge also will be as a point somewhere on this edge. Now, what would this edge correspond to? You're right. So it would be this edge, and then this would correspond to the edge over here. Okay. The vertical over here, we are not worried about that because it will show up as a point. Okay. How about this edge? So essentially, you will be extending this edge further. This vertical again will show up as a point here, and this edge would essentially be shown like this. And then how about this edge? It will be here, and essentially you will get an outer loop. Anything else? Yeah. So you will be seeing this edge as well, and this edge as well. So this is how the victory stand is going to be looking from the top. Now how about we rotate this about the z axis and try to look at the object from this side, standing over here. What do we see? We are essentially going to be looking at the YZ plane. There you go, the YZ plane. What do you see? You would see first this edge, then the two vertical edges, then this edge essentially over here. So this loop is represented over here, and then how about this part? You will have another vertical edge, this one over here, and the horizontal edge there representing this loop. Okay. Now would there be anything that you would be seeing from this side? Yeah, possibly not. Now what if I tell you that let this not be a solid box, but be a box made of, say, glass? Okay. So instead of this being a solid box, this is actually a transparent box. Now focus on this edge. Would you be seeing this edge? Looks like you would be. And this edge would be at some height different from this edge. Okay. So we already have captured this edge here. Now this height is different. Okay. And since this edge is not directly visible to us, we are going to be using a convention. We are going to be representing that using a dashed line. All the other edges which are visible to us, they are being represented as solid lines. All the features which are not directly visible to us, but they are there, they are going to be visible, or they are going to be depicted using dashed lines. Okay. Anything else? Possibly not, because this edge is concealed behind this edge. This edge here is concealed behind this edge, and this edge is actually hidden behind this edge. So we are fine. Okay. Now, so let's imagine that we have an object over here, and that's enclosed by, let's say, a glass box, or a box, or maybe just three planes. This vertical plane here, the vertical plane here, the horizontal plane here, and all these three planes happen to be mutually orthogonal or perpendicular to each other. Okay. Now just follow the animation. Now just imagine that we have light bulbs on all these edges, and they are emanating light in such a way that this light is essentially going to be going in three mutually perpendicular directions: along this direction, along this direction, and along this direction. Okay. So there are special kinds of light bulbs. Okay. So if you look at the rays which are parallel to this edge, you will essentially be having this loop getting captured on this vertical plane. Likewise, if you have rays emanating from these special light bulbs along this direction, then you will have one loop getting captured there, another one there, and the third one here. And in case the light is parallel to this edge from this box, essentially you will be having this big loop getting captured, the smaller loop getting captured. Okay, and if you look at this edge over there, it's kind of not visible from this side, but still there. It's always a nice idea to represent what is also not visible but there. So even this edge is going to get captured. Okay, so the object from this side is going to look like this, the object from the top is going to look like this, the object from this side is going to look like this. Okay, we'll do this exercise at home, so it's a pretty simple exercise for you. All right, so once we have captured these images from 3 different directions, okay, I'll rip this edge off and I'll rotate these planes, okay, so that they happen to lie on the same plane, 2-dimensional plane. So if I rotate this plane about this hinge line, and if I rotate this plane, so this vertical plane is like here, the horizontal plane is like this. I'm rotating the horizontal plane like this, and this one over here, I'm rotating it, like this, like this. All right, so if we flip these planes so that they lie on the same 2-dimensional plane, okay, let's see what we're gonna get. So this vertical plane will be over here. The horizontal plane is going to be on top of the vertical plane, and the right hand side plane, the plane on the right hand side, will be over here on the right hand side of this vertical plane. All right, so we'll see this part over here, these 3 loops over there, and this part over here. So this is the front view if you are viewing the object from this side, the top view if you are viewing the object from the top, and the right hand side view if you are viewing the object from this direction. Okay. All right, so this is the hinge line that separates the horizontal and vertical plane, this one here, and another hinge line that separates the vertical plane and the plane on the right, which is this hinge line here. Okay, so let's get rid of these planes, and this is how we are going to be, seeing the representation of the object in 3 different orthogonal directions. Okay, the object, the 3 different views of the object. So these are the orthographic views of the object. Okay. All right. Of course, this was the first exercise on orthographic views for you. Now, let's try to correlate different vertices and different edges, okay, of the representations in the 3 planes. So, of course, these vertices and the edges will get correlated. So with these, and these, all right. And if we correlate the edges and vertices in these 2 views, we'll have this correlation here, this correlation, and if you look at this edge will get correlated to this hidden or dashed line there. Okay. And of course, there would be a correlation between the top view and the right side view as well. Okay. Now, try to figure what angle this is. Guesses? This would be precisely 45 degrees. Why? Because this distance is the same as this distance. So that's the xy plane, the top view, the xz plane, the front view, and the yz plane, the right side view. As I said before, you don't need to, in fact, you will not be requiring to depict these planes in your orthographic views. This just for your understanding, just for your comprehension. So given the views, so by the way, I make a lot of mistakes, so there's this projection line which is missing over here. Anyways, so think and analyze, there's a question for you. So given the views, can one uniquely determine a three-dimensional object? For you to answer. And a related question, do I need to have all the three views? So if the answer to this question is yes, do I need to have all the three views to be able to uniquely represent a three-dimensional object, or in all cases, or perhaps in some cases only two views would be adequate? Going back to the examples that we were discussing, quite a while ago. So this object, if I look at this object from the front, this is what the view is. From the top, this is what the view is. And from the side, this is how the object looks like. And if we correlate using the projection lines, this is how you would want to draw these projection lines. Okay. Second object, the front view, the top view, the right side view. And if you correlate different features of these objects in different views, this is how your projection lines are going to show up in your drawing. Third object, if this is the front view, this is how the object is going to look like in the front view, the top view and the right hand side view. If you again correlate different features of the object in three different views, this is how the projection lines are going to look like. In every instance, this angle or this line will be making a 45-degree angle with the horizontal line. So if you recall, I had talked about Gaspard Monge, engineer in French military, who was the inventor of descriptive geometry, and he was a person who could formalize drawings by means of orthographic views. So this is the thing which is of importance to us. Monge formalized the technical drawings, what we know as orthographic projections. Yeah. If you are given the three views of different objects, it is possible for you to reverse engineer and try to estimate how, not try to estimate or predict, but try to actually exactly know what the object is going to look like in three dimensions. Like in this case, for example, if this is the front view, the top view, the right side view, this is how the object looks like. This is just a pen, front view, top view, the right side view. This is how the object looks like. It's pretty much like a stool, front view, top view, the right side view, the object. And the front view of a personal computer, the top view, the right side view. This is how 3D objects would look like. So it looks like if you are given these three views, it looks like, as I say, I could be wrong, and something that you need to answer for yourself. So given three views, given three orthographic views, it should be possible for you to exactly extract the three-dimensional information of an object. So this was an exercise that one of my students, Amitesh Mishra, did quite some time ago, in probably 2005, 2006. He did a fantastic job. Okay, one thing I would always emphasize throughout this course: sketch, 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 and sketch, and sketch. Keep sketching, because that's how you practice. The more you practice, the better you become in drawing. Okay? Always a good idea to sketch before you start representing an object via its orthographic views and other views as well. So let's take an example. So this is a three-dimensional object we have. This is about 100 units, millimeters, 80 millimeters. The height is about 60 millimeters over here. Okay. So this is a feature which is cut from the block, and we would like to represent this object by means of orthographic views. Okay, so let's see how. So the arrow means that this is the front view. So the moment this is the front view, in the third angle projection, we are going to be talking about that later, this would become the top view and this would become the right hand side view. Okay. All right, so with the front view given, how would the object look like if we visualize the object along this direction? Again, so mark the way I am representing these edges. So at this time I am just constructing, I am not constructing the final drawing at this time. So if I am using construction lines, I am going to be using a 2H pencil or 2H lead, ensuring that my lines are very dim, so barely visible. Okay, so this horizontal edge would correspond to this edge, the vertical edge would correspond to this edge. If I look at this object along this direction, this entire feature will be represented via this edge, and of course there will be a horizontal edge, this guy here. Always a nice idea to start with the bounding boxes in the corresponding view. So this actually is the bounding box for the front view. Let us also draw the bounding box in the top view. So the length is 100. Okay, in the top view I am going to be representing this edge, so it's about 80. So this block is 100 by 80, and I'll draw a vertical hinge line separating the front view from the right hand side view. I'll draw the projection lines. Okay, so this height is 60. Now this length would correspond to this length over here, which is this length, it's about 80. Okay, so this is the bounding box of the object if I am visualizing it from the right hand side. Okay, so this of course box is 100 by 60 in dimensions, the length and the height. So once I have identified the bounding boxes, let's try to sketch all the features after of course I complete the entire schematic including the projection lines. Alright, so this edge is this one, vertical edge is this one, and then this is about 20 from there. Then I am going down, I am going up from here, I am going leftward from here. Okay, so what would be this length? It's about 80, and then I am going vertically upward. Yeah. Okay. Now what else do I see? I see these steps at heights 40, 50, and 60. Okay, but we'll come back to that later. Let's try to look at the object from the top. I have drawn this edge. Okay. Now it's always a nice idea to work with the projection lines because you are kind of sure which entities or which features of the object you are representing in whichever view. Okay, so I project this point upwards, and then I show this edge, and then I have got to show this edge over here, but we'll come back to that later. Shown this edge here, this edge here, this edge, and then I'm going down from here to here, this edge. All right, and then of course this edge is going to show like a vertical edge in the top view, and of course this entire thing. So this edge would be this and this together. Now this one here corresponds to this edge. It's about 20 plus 25, 20 plus 25 downward, and then I've got this edge right there, which is 20 further downward. So looks like I have been able to capture all features of this object in the top view. Once I have done that, I'll start using my projection lines. I'm working with the right side view, this edge, this edge here, this edge here, and then I'm projecting this feature onto the right, again that feature and this feature, all these three features, and then I'm going to be projecting these features downward. Okay, I'm going to be ensuring that I maintain the heights. So this height is about 60, this height is 50 here, this height is 40 here. Okay. Correspondingly, I'll go to the front view and draw these lines. Finish the vertical edge, which would correspond to this edge in the front view. Of course, I should have drawn these projection lines a little earlier, and then I'll finish off the right side view. Am I done yet? Possibly not, because I'm missing this edge and this edge. There I go. Okay. Anything else that I'm missing? You know, there are a lot of chances that you're going to be making mistakes when you're drawing, you know, when you're working with these technical drawings. So these projection lines are going to be helping you out in identifying those mistakes. So if you're missing any feature in any one of these views, after you have drawn these projection lines, you will know for sure what you have missed. So you've got to be a little careful. You've got to be very careful and sketch, 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 and sketch. Practice and keep practicing. This is what the golden rule in technical drawing is. Done? All right. Relax. Keep thinking and analyzing.